So when you're asked to write an electron configuration of an ion, my recommendation, strong recommendation, especially if it's a cation, is to write out the electron configuration of the neutral species. For anions with the negative charges, you just throw in some extra electrons, you can count by the block method. The anions aren't problematic. However, the cations, write out the full electron configuration. So for instance, with vanadium, if it was neutral, I would have argon, 4s2, 3d3. So just like we were doing in the previous exercises, who are our valence electrons? So I would identify the 4s2 as my valence because it has a higher principal quantum number. Therefore, when I do the 2+, I'm going to lose the 4s2. So the electron configuration of vanadium 2+ is argon 3d3. You're going to lose from your valence. All right, let's look at potassium then. As a neutral species, I would do argon 4s1. So when it's potassium plus 1, it's going to be isoelectronic with argon. So iso means the same, and electrons, right? Same number of electrons. So these two things have the same electron configuration. For iron 3+, for the neutral iron, it's argon 4s2, 3d6. So here's an interesting example. We see that the valence is the 4s2. And that's going to drop out as we're trying to obtain a +3 charge. After that, we don't have a choice but to take another electron from the 3d. And so the 3d would go down to a 3d5. So you might be wondering, why does that happen? I mean, we've seen a +2 with iron, and the +2 is easy to justify, right? We just are taking away the valence shell. But why does it do a 3d5 or a +3? And that's because there's increased stability associated with half-filled subshells. So I'll do something like this. Argon, and then we have our 3d, and then 1, 2, 3, 4, 5. So this would be for iron 3+. And once again, there's a greater level of stability associated with half-filled subshells. You're minimizing electron-electron repulsion. So if we kept it at 3d6, right, then those two negative charges are in the same orbital. They're fighting for the same space. So it makes sense that a +3 can happen. Everything that you see happen in chemistry is motivated by an increase in stability. Or an increase in entropy. I shouldn't just say that, but all right, hafnium. As a neutral species, we have xenon. We're in the 6th row, so we're going to do 6s2. We're going to fill up the whole F block, 4f14, and then I come back up and I need 2 electrons that I need to put into the 5d block. So that's as a neutral species. So valence is going to be our 6s, but we need to lose 4. So we're going to lose from 6. Next, we're going to lose from 5, because 5 is higher than 4. What else is happening, though, to emphasize this increase in stability, as a cation, the hafnium is left with a full subshell. And that also is a very stable place to be. You can look it up. There's a bunch of different ions that are transition metals can form, and maybe hafnium 2+ is a possibility. But if you have a 2+, then you still have this 5d2 hanging about, and it's just kind of messy, so, and unstable. Not completely unstable, but it's more stable to get rid of it and have a full subshell. Last one, nickel. We got argon, 4s2, 3d8 as our neutral electron configuration. Our valence is the 4s2. So my nickel 2 plus is going to have an electron configuration of argon 3d8. Real quick here, let's go over two different definitions. We have this idea of paramagnetism, when something has unpaired electrons and then it's attracted to a magnetic field. So I had trouble remembering this as a student until I realized that para, the Spanish word for for, is in this, and then I started thinking of it as for the magnet. Diamagnetism occurs when there's no unpaired electrons. So the sum of your MS values equals 0. All of the spins are canceling one another out in the case of diamagnetism. We've been asked to identify or predict if cobalt 2 plus and nitride will exhibit paramagnetism or dimagnetism. We can test this in real life. It's super cool. So for something like cobalt 2 plus, you would grab the salt of the ion. We could use like cobalt 2 chloride. And then we just put the salt in the vicinity of a really, really strong magnet. You can't just use like a refrigerator magnet. It has to be a super strong magnet. But you'll actually see the salt gravitate towards the magnet, adhere to the magnet. It's really, really cool. So I took the liberty of writing the neutral cobalt. And for cobalt 2 plus, we want to get rid of that valence. So the electron configuration of cobalt 2 plus is going to be argon 3d7. And at that point, if you can't see it, draw out the d orbital and put your 7 electrons there. So cobalt 2 plus has 3 unpaired electrons. It's also true to some extent that if you have more unpaired electrons, so say you have 4 or 5 unpaired electrons, you're going to be more magnetic or more attracted to that magnetic field. Versus something that I've had a lot of trouble with it too, trying to visually see it in real life. If you just have 1 unpaired electron, forget about it. In theory, it should be paramagnetic, but with that 1 unpaired electron, it's not really enough, at least with the magnets I have, to see that actually happen. So more unpaired electrons, more magnetic. We have nitride. And I did write the neutral one. However, when you're adding electrons, you just throw them into the last subshell that you're using. So this is going to be helium 2s2, 2p6. And I'm going to draw out the whole valence shell real quick here. So we have 2s and 2p. And it looks like everybody is paired up in that valence shell. We have no unpaired electrons. So something like this is going to be diamagnetic. And this one up here, because of the 3 unpaired electrons, is paramagnetic. Typically, I ask students to know 5 different anomalies, which are just exceptions to the order of filling that we would expect with our electron configurations. So there's 5 in the main part of the periodic table, and then there's something like 20 plus exceptions if you include all the exceptions that we see in the F block, in the inner transition metals. But I try not to go there too much because that's overwhelming, and again, it's not that predictable. However, the 5 that I like students to know are predictable if we start thinking about why do these exceptions occur. So I had you all write what you would think would be the electron configuration of silver. So I imagine most of you wrote 5s2,4d9. Let's do a little energy diagram for the valence electrons of silver. So krypton, nothing interesting going on with the core, right? And then we have 5s2. And if you take a look at your energy diagram, the energy difference between 5s and 4d is not that significant, right? So we have a very small energy difference. I'm going to put my 2 electrons here, and then my 9 electrons in the 4d. So what's happening here, and why is silver an anomaly? Well, there's so much stability to be gained if you have a full subshell. And there's such a small energy difference. And the 4d is only 1 electron away from having a full subshell. So this electron that we would think would be in the 5s actually moves over to the 4d. And that creates this full subshell. Our core is full. And then we just have a random electron hanging out in the 5s1. So let me cross this one out because this one's wrong. Silver, the correct electron configuration will be krypton, 5s1, 4d10. And the fact that you had to memorize, 99.9% of the time, silver does a +1 charge. Why? Well, we see that now because its valence only has 1 electron, and getting rid of that would mean that all the subshells, all the shells after that are nice and full and stable. So besides silver, everyone in that same group there will exhibit a similar anomaly. So we see the same anomaly with copper and gold as well, where you're going to have NS1 and -1 D10 as your electron configuration. For chromium, I imagine you all wrote down this. Let's do the same kind of analysis. We have argon, and then our 4s, and then very close in energy, our 3d. The fact that the energy differences are so small as we get to the higher parts of the energy diagram are critical to this being able to occur. You're not ever going to promote an electron from like a 1s to a 2s just because, right? Maybe if there's energy coming in, it might happen, but it's not just going to be rearranged on its own. So we see that there's 2 electrons in the same orbital, and then there's a whole bunch of singles, and then there's an empty orbital. So it's almost like the 4s and the 3d are a single subshell, and we just fill singly going across. So we have all singles. And we've minimized electron-electron repulsion by doing that, by giving everybody their own space. It's almost like the most extreme example of Hund's rule, right? And the energy difference is so small that we're thinking of it almost as a degenerate set of orbitals. So this is wrong. And we're going to do argon, 4s1, 3d5. Apart from chromium, we also see this with molybdenum. And I can kind of generalize it to say we're going to have NS1 and -1 D5 as our generalized electron configuration.